Hello, differential equation students. Topic 24 is an introduction to systems of ODEs, ordinary differential equations. Now, a system of ODEs is a collection of ODEs involving multiple functions of one variable. The order of the system is the highest derivative present. The dimension of the system is the number of dependent variables involved, or you can say the number of functions involved. If the dimension is 2, we call the system planar. And finally, the system is autonomous if the ODEs do not explicitly involve the independent variable. So we're going to fill in the table below. Assume that t is the independent variable in each case. So our first system has two equations. First equation is x prime, and we're assuming that means x prime of t, is equal to 2y plus t. Now y and x are the two dependent variables involved in the system. They're the two functions of t, and t is the independent variable. The second equation is y prime is equal to sine 3t. All right, so the first thing to identify is the order, the highest derivative present in the entire system. And the first equation has a first derivative, and the second equation has a first derivative. So the highest derivative present is 1. So we say the order is 1 in this case. The dimension is the number of dependent variables involved, and that's x and y. T is the independent variable. So every time you see a y in the statement, like right here, 2y, that's really 2y of t. So we have two dependent variables, x and y, so our dimension is 2. Is the system autonomous? Well, that will depend on whether or not the equations explicitly involve the independent variable. Well, the independent variable is t, and this equation explicitly involves it, and so does this equation. So it's involved in both equations, so we would say that this is not autonomous. Let's move to the second example. Two different equations. T is the independent variable, and I see x's and y's otherwise. So we have two dependent variables, x and y. And the highest derivative I see present is y double prime. So this would be a second order system. And again, the dimension is 2 because there are two dependent variables, x and y. And autonomous, the answer is no, it's still not autonomous because there is an explicit variable involved right here. So no, it's not autonomous. Now we have three equations in our system. And we see x, y, and z are the dependent variables, and t is still the independent variable. And so we have that the order, scanning for the derivatives. The highest derivatives are first derivatives. They're all here on the left side. So this is still a first order. And we have three dependent variables, x, y, z. And do any of the equations explicitly involve t? Well, yes, there's a t here and a t here. And so we have, this is not autonomous. And then finally, we have another system of three equations. This time I'm using x sub 1, x sub 2, and x sub 3 to represent the three dependent variables instead of x, y, z. And the highest derivative present I see is first derivatives, again right here. So we have a first degree system. Again, it's a three dimension because there's three dependent variables. And then is t anywhere explicitly in these equations? And looking over on this side, there are no components that explicitly involve t. So this one is yes, autonomous. Now, of these four systems, which ones are planar? Well, every time the dimension is 2, we would have a planar. So these first two are examples of planar systems. Dimension 2, two different dependent variables, x and y in those cases. Okay, next slide. Use technology to find the solution to the planar system of differential equations with initial conditions below. Verify that the solution is valid. Okay, so here we have a system. This is a planar system, first degree, first order, and it is planar, so dimension is 2. And we also have some initial conditions of what x and y have to be at time 0, at t equals 0. And I'm going to use Wolfram alpha to find the solutions, and I've already typed it in. I just got to bring it up. Notice what I've typed in here. I wrote the word solve, and then x prime equals, and then my equation, and then comma, then y prime equals, and my equation, comma, and then my initial condition for x, comma, and my initial condition for y. And then I just hit enter. And look at the results it gives me. It gives x of t equals 6e to the 2t minus 4e to the 5t. Now I'll enter those answers in my notes here. So the solution, according to Wolfram alpha, is that the x function as a function of time is equal to 6e to the 2t minus 4e to the 5t. And the y solution was 3e to the 2t minus 4e to the 5t. Okay, we're going to verify that this is in fact a solution by first verifying the initial conditions. So let's do that part first. If I plug 0 in for t in the x function, we get 6e to the 0 minus 4e to the 0. That's just going to be 6 minus 4, and we get 2, so check. And then let's verify that when you plug 0 into the solution, you get the correct initial y value. And 0 in for t, so we have 3e to the 0 minus 4e to the 0, so that's just 3 minus 4, which is negative 1. So initial conditions are met. Now we want to verify that the differential equations, the system, is also satisfied. Both of these equations here and here. So we're going to do x prime, and then we're going to calculate this side and see if we get the same thing. So let's do x prime first. The derivative of x with respect to t, use the chain rule. Derivative of 6e to the 2t is going to be 12e to the 2t. And then the derivative of negative 4e to the 5t will be negative 20e to the 5t. So this is what we get when I do just x prime. But now let's do this side, negative x plus 6y, and see if they're the same thing. So let's do the opposite of x. So that's going to be negative 6e to the 2t plus 4e to the 5t. And then add to that 6 copies of y. So I'm going to distribute the 6. I'm just going to do 6 times this y function and distribute the 6. So we have plus 18e to the 2t minus 24e to the 5t. And the question is this statement for x prime and this statement for negative x plus 6y, are they the same? Well, we just have to combine some terms here. For example, I see that we have negative 6e to the 2t plus 18e to the 2t. Combine those, that gives me 12e to the 2t. So that matches this part. And then we have 4e to the 5t minus 24. That's going to be minus 20e to the 5t, which matches this part. So these are the same. So that works. Now we have to verify that the second equation in our system is satisfied. So let's do y prime. Looking at my y function right here, and do the derivative, use the chain rule, we're going to get 6e to the 2t minus 20e to the 5t. That's doing the left side of the second equation. Now let's write down what the right side would be. Negative 3x plus 8y. Negative 3x. So I'm going to distribute the negative 3 across the x function. Negative 3 times 6e to the 2t will be negative 18e to the 2t. And then we're going to get plus 12e to the 5t. And I've done this part. Now let's do plus 8y. So I'm going to distribute 8 across this y function. So we're going to get 24e to the 2t. And then minus 32e to the 5t. And again, the question is going to be similar to before. Is y prime the same thing as negative 3x plus 8y? Well, let's gather the e to the 2t terms first. So we have negative 18e to the 2t and 24e to the 2t. Add those together, we get 6e to the 2t, check. And then we have 12e to the 5t minus 32e to the 5t. That gives me negative 20e to the 5t. So yes, these are in fact the same. So we have verified the initial conditions and the differential equations. They're all satisfied by this solution. So thank you, Wolfram Alpha, for doing that for us. Now these solutions are plotted below against t. So here are the two solutions, x and y, and they're plotted against t. Without technology, plot the path of the solution in the xy plane. So over here I have an xy plane where t is not explicitly visible here as an axis. And what we're going to do is track as t varies between 0 and 2. We are going to track the path. We're going to track the x and y coordinates and then track the path when you plot the xy coordinates in the xy plane. This is also called a phase plane plot. X and y are both functions of t, but when you remove t from it and say what is that relationship between x and y as t varies, we're going to get this phase plane plot. And we'll use technology to confirm. Okay, so by hand, first of all, I'm going to make a little table here in the middle that keeps track of t, x, and y. And we're only going to worry from t equals 0 to t equals 0.2. So if I look at when t is 0, right, imagine this, going to move this line right here around at different times and get different outputs for the two different functions, the red and green. But when t is 0, when you plug 0 into the red function, you get 2. So when t is 0, you get the red function outputs 2. So that's the x-coordinate. But the green function will output negative 1. So you can think of t as time if you'd like. At time 0, the x is 2 and the y is negative 1. So we can go to our phase plot and plug in that point. So right here is when t is 0. We're at 2, negative 1. And now we're just going to, you can pause this orange line anywhere you want and then write down the coordinates. I'm only going to do some of these For example, when we're at 0.1, when t is 0.1, what does x appear to be? Well, we're going to estimate this. It looks like if you zoom in right into this area right here, we get an output that's less than 1. So about, let's say 0.8, just to approximate. So x is about 0.8, and y is approximately negative, maybe it's not quite -3, but we'll say good enough, approximately -3. And all of these are approximate. We're just eyeballing this. So now we want to plot that point, 0.8 comma -3. So that's somewhere in this area. And this was at t equals 0.1. And as t advanced, our solution path certainly connected these dots, something in this manner, because we can see over here that all that happened was that x and y both, between t equals 0 and t equals 0.1, the red and the green functions both simply decrease. And so we would have some sort of a behavior like you see right here in our phase plane plot. Now, another point of interest might be where we get a 0 involved. So that looks like approximately t equals 1.4, or 0.14, I should say. And at that t, it looks like the red output is 0, so the x will be 0, and the green output is approximately -4. So 0 comma -4 is a point, is right here, and that's when t is approximately 0.14, and we can suspect that we just kept continuing, both x and y kept continuing to decrease to get to that point. In fact, just looking at this graph, x and y continue to simply decrease, and so we expect our image over here to continue to move in the southwest direction. And let's just do one more. Let's drag this to when t is 0.2. So in this area here, when t is 0.2, and we'll stop there. The x, the red output, is approximately -2. So we'll say x is about -2. And the green looks like about -6.4 or so. Just guessing, -6.4. So -2 and -6.4. So we're roughly in this area right here. And this is when t was 0.2. And our curve continue to move in the southwest direction. All right, so this is done without technology, just looking at the graph of x and y against t, and for various values of t, tracking what x and y are, and then plotting that path in the xy plane. This is the same thing you might have done in a Calc 2 class when you did parametric equations. Now I'm going to move over to Desmos and open a file that I already entered. So there's the red and the green. If I hit the home button, you can see that the functions are very dramatic. So I had to do some level of zooming to see the same scale that we had before. So here we go. They're the functions x and y with respect to t. Now here I'm calling them f and g. Desmos doesn't like when you use x as a name of a function. So I just went with f and g, but f stands for the x function and g stands for the y function. And then in Desmos, to make a parametric plot in the xy plane, you have to type in what you're seeing here in the third line. I'm going to reveal that image right now. This is f of t comma g of t. You put the x function in, you essentially type a point, parentheses, space, comma, space, parentheses, and in the x position you put the x function, and in the y position you put the y function. And then you specify the values of t for which you want this graph. And I said little t is from 0 to capital T, but then I added a slider for capital T. That's the 5th line here. And that slider for capital T down here, you can do different values of capital T. I let it vary up to 0.2. And then I made a 4th line here that's f of capital T comma g of capital T, and I turn the label on. That's going to track up the point as time advances. So let's go ahead and hide the f and g functions now. Let's just hide those. Let's click the home button, go back to our normal scale. Reveal the point as well, there we go. And then let capital T vary, and you're going to see that this animates as time advances from 0 to 0.2. And we can change how that advances, only going forward, for example. That more or less mimics what we guessed, what we did by hand. Okay, let's go to the next slide. Higher order ODEs can be expressed as first order systems of ODEs. So this is interesting. So we've seen some higher order differential equations in the past, but now we're going to show you a way to change it so that's a first order system of ordinary differential equations. So express the third order ODE with initial conditions below as a system of first order ODEs. Okay, now the way what we are going to do this is we're going to take this third order ODE, and the first step I want to do is we're going to solve for the highest derivative. So solve for highest derivative. So solve for the x triple prime. So I'm going to subtract all the other terms over to the other side and divide everything by 3. So I'm going to do this all in my head. So we get x triple prime is equal to, and then on the other side, we would have a -2x double prime and divide by 3. We're going to have a negative 5x and divide by 3. And we're going to have that 7t that's over there divided by 3. So plus 7/3 of t. So we solved for the highest derivative. That's our first step. The second step is going to be to define new functions. And because we have 3 derivatives, we're going to have to define 3 functions. We're going to create this, we're going to turn this third order ODE into a 3-dimensional system of first order ODEs. And the way to do this is we're going to let any variable you want be x. And so I'm going to use new letters here. I'm going to say that u sub 1 is my x function. Now, the next function I want to define is going to be u sub 2, and it's going to be the first derivative of the x function. And then u sub 3 will be the derivative of that. So it's going to be the derivative of the second one, which is x double prime. Okay, now that we've created our new functions, we defined our new functions, go ahead and define their derivatives real fast. So u1 prime will simply be x prime. u2 prime will be x double prime. And u3 prime will be x triple prime. And this is going to be the key for setting up or creating our first order system. So we're going to do that last. So step 3 is to create the first order system. So we have u1 prime is equal to x prime, looking at this statement. But x prime is the same thing as u2. And so keep in mind when I'm doing this, I want to create a system that only involves the dependent variables and potentially the independent. Well, the dependent variables now are going to be these 3 u's. So I don't want any x's in my system. I only want u's, so the u1, u2, u3, and potentially t's. So keep that in mind as you're doing this. Now u2 prime, our second first order differential equation, u2 prime is x double prime, but x double prime is the same thing as u3. So I get u3. And finally u3 prime is x triple prime, but x triple prime is given by the original ODE, given by this statement. And furthermore, x double prime can be written as u3, and the x here can be written as u1. So I'm going to rewrite this statement right here, but I'm going to put a u3 right here for x double prime and a u1 here for x. So we wind up getting negative 2/3 of u3, negative 2/3 of u3, minus 5/3 of u1, and then finally plus 7/3 of t. And there's our system of 3 equations. They're first order because the highest derivative present is a first derivative, and it involves only the dependent variables u1, u2, u3, and also the independent variables involved. So this is not autonomous because the independent variable is involved right here. And then of course our initial conditions, we've got to reframe it in terms of u1, u2, u3. So we know that u1 at time 0, well, u1 is the same thing as x. So u1 at time 0 is the same thing as x at time 0. So we want u1 of 0 to be 4. u2 at time 0, well, u2 is the same thing as x prime. So x prime at time 0 is negative 1. So u2 at time 0 is negative 1. And then finally u3 of 0. Well, u3 is x double prime, and x double prime is 6 at time 0. So u3 at time 0 of 0 will be 6. And there's our initial conditions expressed in terms of u1, u2, and u3. All right, let's go to the next slide and talk about what it means for a system to be linear. Now, a first order system is linear if it can be expressed as demonstrated below for the planar case, and which generalizes to all dimensions. So I'm just giving you an example of what a planar or 2-dimensional linear system looks like. So we have just 2 functions, x1 and x2, and their first derivatives isolated. And then over on this side, we have a potential linear combination of x1 and x2. So we have an a11 and an a12. This just means the first equation, first entry, first equation, second entry, second coefficient. This a21 was second equation, first coefficient, second equation, second coefficient. And notice what makes this linear is the fact that there's no powers on these dependent variables other than 1. Right? There's implied 1 powers on those. So this would be nonlinear if there's a square here, for example, or if there's a square root on that dependent variable, would make it nonlinear. Also, if you had like a A11, X1, X2, the product of these two dependent variables would make this nonlinear, so that's a problem. So it has to be of this form. So some sort of coefficient times the first dependent variable plus some sort of coefficient times the second dependent variable. And since this is a planar system, there's only two dependent variables. And then plus potentially some other function off here on the side. And same thing is true for x2 prime. It's some sort of coefficient times the first dependent variable plus some sort of coefficient times the second dependent variable plus some sort of function over here. Now, some comments on these coefficients. These coefficients, the A11, A12, A21, and A22, all the A sub ij's, and also the forcing terms, these are called the forcing terms, can be any functions of t. So these don't have to be constants. They could be functions of t. Same with those and same with these. Now, if they are constants, if all the coefficients and forcing terms are constant, reading this, then the system would be autonomous, because the independent variable t would not be explicitly stated anywhere. Also, we say that if all the forcing terms are 0, then the system is homogeneous. So if these are both 0 and they're not there, then we say the system is homogeneous. Now, in matrix form, it looks like the following. You take the two derivatives, the x1 and the x2 derivatives, and create a vector out of it. So this is a 2x1 matrix right there. And that's equal to. Then you do the square matrix of the coefficients, A11, A12, A21, and A22. And that gets multiplied by a 2x1 vector of the functions, x1, x2. And then to that, you add a 2x1 vector of the forcing terms. Now, matrix multiplication. If you were to multiply these two things here, if you'll recall, you would grab the x1, x2, you would drag them up here, x1 and x2. You would then drop them onto the rows of this matrix here, the coefficient matrix, multiply the entries and add the results. So when I drop x1 and x2 on these coefficients, you really wind up with this component of our differential equation. And when you drop the x1, x2 down onto this row, you wind up with this component of our differential equations. So this product right here will yield a 2x1. And then you add it to this 2x1, and that really just tacks on the f1, f2 at the ends of these statements. And so these linear systems of equations can be expressed as in matrix form as a product of a coefficient matrix times the column vector of dependent variables, and then add the forcing terms to it at the end. And then to be more concise with this, we're going to call this vector of functions a vector function, and we're going to use a bold X or an X with a bar above it to represent that. So here this is using bold terms, and here this is using the vector notation, bars above the variables, to indicate that we're thinking vectors. And the bold is sometimes hard to perceive, and so it can be confusing. You can look at that x and think it's a scalar, but that x there represents a vector. It represents this vector. So we have and to differentiate a vector, you just differentiate term by term. So when I say, what's the derivative of x vector, and the x vector is x1, x2, then you just differentiate the two terms. So x vector prime is this, is equal to the coefficient matrix A, which is the matrix of coefficients right here, times the vector function x, and then plus a forcing vector plus bold f, and that represents both of these. So get a little bit of practice here. We're going to express each linear system in matrix vector form. Okay, so I'm going to write the left side as a vector instead. So u1 prime and u2 prime is equal to, and there's going to be a coefficient matrix. Now, things you have to be careful about is that the u1 coefficients are lined up. Notice up here that the x1s and the x2s line up correctly so that the matrix of coefficients winds up oriented correctly. So we have to do a little bit of unscrambling here. Notice the u1s are not lined up currently. So you want to put the u1 coefficients in the first column, so 5 and -8. So just be careful about that. And then you want to put the u2 coefficients in the next column. And the u2 coefficients are t and 3. And then you multiply this by the column vector of functions of the dependent variables, which is u1, u2. And then to this, you add any terms that don't involve the dependent variables. And notice there's nothing added here, nothing added here. So the forcing terms are 0 in this case. So this is a homogeneous system. And now you can say instead, it's hard to do bold with writing. You have to just do something like this to make a bold. So that's why they have the other notation. I'm going to use the bar notation. So this matrix here in the front we'll call matrix A, the coefficient matrix, and then times the u vector. That's the u1, u2. And this is equal to the u vector prime. So in super concise notation, it would look like this. U vector prime equals matrix A times u vector. Notice that this is not this is not autonomous because t, the independent variable, is explicitly involved. If that t was a constant, then this would also be autonomous. Not to be confused with homogeneous. Homogeneous is whether or not there's a function over here being added, a vector function being added to all of it. And autonomous is dependent on whether or not any t's are explicitly involved. All right, the next example, we're going to write this in terms of a vector. So we have x, y, z, and all of these are primes, equals. And then we're going to have a 3 by 3 coefficient matrix. And make sure, again, you do the alignment. So all the coefficients of x you put in the first column. So that's going to be 1, 1, 6. Then the coefficients of y. Notice these terms don't have any y's, so that just means you're going to have a 0 coefficient of y, a 0 coefficient of y, but then the third equation has a -1 coefficient of y. So these are all the coefficients of y. Now we do all the coefficients of z. We have a -9 coefficient of z. There is no z in the next two terms, so they're going to next two equations. So you're going to get 0 and 0 as the coefficients of z for the second and third equation. And then that's all times the column matrix or column vector of just the dependent variables x, y, z. And then we look for any forcing terms. Are there any terms involved in these differential equations that were not coefficients of x, y, or z? And the ones that stand out to me are the 3 root 2 and the 4. So we have to account for those still. So we need to add an extra vector, column vector over here. And in the first case, there is everything is accounted for. All the terms of the first equation involve a dependent variable, a coefficient and a dependent variable. So the forcing term of the first function is 0. But the second equation has this 3 root 2. That's not a coefficient of x, y, or z. So we need to have that involved by adding the second forcing function is this 3 root 2. So that needs to be in this position. And then in the third equation, we have this 4, free floating 4. That needs to be right there. So this is how we express this system in matrix form. And I'm going to call the matrix of coefficients A. This vector right here, I'm going to call it the x vector. So x vector, that represents the x, y, z. Plus, and then we had a forcing function over here, three forcing functions. They're all constant, by the way, but that forms a forcing vector. And then over here we have the x vector that's being differentiated. So this system is not homogeneous, so we can say it's non-homogeneous or inhomogeneous because we have a non-zero forcing function over here. But notice that all the coefficients are constant and all the forcing terms are constant. So this one would be autonomous because t was never explicitly mentioned or involved in any of these equations. So this is autonomous but inhomogeneous. And the other one was homogeneous but not autonomous, referring to this one. So let's summarize this. We have homogeneous but not autonomous. And this one here we have inhomogeneous and autonomous. Okay, so let's just practice this idea a little bit more. On the next slide, determine whether each first order system is autonomous, whether it is planar, and whether it is linear. If it is linear, determine whether it is also homogeneous, and assume t is the independent variable in each case. Now, we're not going to write any of these in matrix form. We're just going to look at them the way they are written. All right, so to determine whether it's autonomous, we look for whether or not t is involved anywhere, and sure enough, I see a couple t's. So the answer is no. And let me color code this, actually. I'm going to say no to autonomous, but then also circle the issues. The presence of these t functions makes it not autonomous. Is it planar? Well, planar means there's only two dependent variables. This one has three. The dimension is 3, so this is a clear case of just being no, not planar. Is it linear? All right, so to identify whether it's linear, look to the dependent variables over here in the right sides of the equations and see if they just have, if they're raised to the first power and potentially with a coefficient. So x1 to the first power, x3 to the first power, x1 to the first power, x1 to the first power, and x2 to the first power, and they all have different coefficients, that's okay, but this is linear. Yes. Is it homogeneous? Well, it's going to be homogeneous only if every term over here on the right side is a term involving a dependent variable with a coefficient. So there's no terms over here on the right sides of these equations that does not involve the any of the dependent variables. Well, in the first equation, both terms involve the dependent variables. In the second equation, this first term does not involve a dependent variable. So let's go with color coding for this part. So this term right here is going to make this non-homogeneous. And in the second equation, this term right here also is going to make the third equation, that t squared term is also the reason why this is not homogeneous. It's a term that does not involve a coefficient and then times a dependent variable. Okay, let's go to the next example. Autonomous. That one's easy. Just look for any presence of t's, and there's a few. This 4t and this 6 radical t makes this not autonomous. Is it planar? The answer is yes in this case because we only have two equations, or two dependent variables, x and y. Is it linear? The answer to linear is going to be no for this reason right here. You have a case where you have a product of dependent variables, and that can't be for a linear system. Is it homogeneous? Well, it's not. We only consider homogeneous, we're only going to define homogeneous for the linear systems. And since this is not linear, we're going to say not applicable as our answer to whether it's homogeneous. Remember, the instructions say if the system is linear, determine whether it is also homogeneous. So once you have nonlinear, don't worry about homogeneous. Let's look to the third one here. We have, do you see any t's explicitly mentioned over here in the right? And I do not. So we have, this is in fact autonomous. Is it planar? The answer is no, because there are 3 dependent variables. Is it linear? Okay, so look to the dependent variables of the first equation. They have 1 powers. Dependent variables of the second equation, well, this one's an issue. This one here has a 1/2 power. So this is the nonlinear component. We're doing linear as orange. So the answer right away is no because of this term right here. This is a u3, which is a dependent variable, raised to the 1/2 power. It needs to be raised to the 1 power with a coefficient, potential coefficient. Another issue is right here. We have a u2 squared. That's another issue why we have a non-linear equation down there. And because it's not linear, then we just say NA for not applicable for homogeneous. Okay, let's go to the next example here. Is this one autonomous? I'm looking at the equation over here, looking for the independent variable t. I don't see it, so yes, this is autonomous. Is it planar? Yes, there are only, this is a dimension 2 because there are 2 dependent variables, u1, u2, so it's planar. Is it linear? Okay, so the u1 to the first, u2 to the first, u1 to the first, yes, and with potential coefficients, so yes, this is linear. Now, is it homogeneous? So we have both terms involve a coefficient times a dependent variable of the first equation. Now, the second equation, only the first term is a coefficient times a dependent variable. This over here is a term that makes this inhomogeneous. So we're going with green for the inhomogeneous part. The presence of this term right here makes this not homogeneous. Okay, let's go to this fifth one. Is it autonomous? Do you see any t's over here? I do not. So we have, yes, it is autonomous. Is it planar? No, because there's 3 dependent variables, not 2. Is it linear? Only one term here is going to be a problem. That one right there is the only term here that's causing this to be nonlinear. We have a square on a dependent variable. If that had been a t squared, then this would have been linear, because you can the functions of the coefficients and the forcing functions can be any function of t that you want. But to be linear, you got to look to the dependent variables, the x, y, z. And do the x, y, z's in every equation have only raised to the first with a potential coefficient? That could be anything. Well, this dependent variable is raised to the 2. So this is the term that's going to violate being linear. So we have no to that because of this y squared term. Is it homogeneous? Well, it's not linear, so we don't bother with the homogeneous. So we'll say not applicable. And let's look at this last one now. Looking to the right, do you see any functions of t? Well, I see a few. So we're using red for the autonomy. Let me go back to red. This e to the t expression, also I see a 5t squared right here. We do see some explicit functions of the independent variable, so it's not autonomous. Is it planar? The answer is no to that as well, because this is a fourth dimensional. There's 4 dependent variables. Is it linear? Okay, so look to the coefficients of the dependent variables, to the x1s, x2s, x3s, and x4s. Here's a 9 in front of an x1 to the first, and here's a function, a coefficient of an x sub 3 to the first. Now remember, the coefficients can be any function, or they could be constant. It's just the dependent variables that you want to be raised to the first with a potential coefficient. So this is a linear equation with respect to the dependent variables. This next one's also linear with respect to the dependent variables. This last one is also linear with respect to the dependent variables, and so is this last one. Right? The coefficients don't have to be linear, just the dependent variables have to be linear. And so we have, this one is linear. Now we want to see, is it homogeneous or inhomogeneous? So if it's homogeneous, then every single term will involve a dependent variable. So this involves a dependent variable, so does this one. This involves a dependent variable, so does this one. All 4 of these do, and both of these do. There's no forcing terms in any of these. All the FIs, the F1, F2, F3, and F4 are all 0. So this makes this one homogeneous. Okay, and that covers several different systems of differential equations and how to classify them. The next slide. 2 or more vectors are linearly independent if and only if no vector is a linear combination of the others. Also, the columns of a square matrix are linearly independent if and only if the determinant of that matrix is non-zero. Okay, so we have this first example here as a matrix, has 2 columns. You can think of each column as its own vector. So the question is going to be whether these vectors, whether these columns, are linearly independent. Now, to determine whether they're independent, when you only have 2 different vectors, if neither vector is a multiple of the other, then the 2 vectors are linearly independent. So the only way to scale 1, 3 to make it look like 2, 5, well, to scale the 1, you would have to double. So if you doubled this first column, this first vector, do you get this one? And the answer is no. The doubling turns the 1 into the 2, but it turns the 3 into a 6. So I can see right away that this column is not a multiple of this column, and vice versa. This column is not a multiple of this column. So I can say that the 2 columns are linearly independent. It's very easy to determine if 2 vectors are linearly independent. Just determine whether or not one is a multiple of the other. Another option you have, since we form a square matrix out of the 2 columns, out of the 2 vectors, is to just do the determinant. If the determinant is non-zero, then the columns will be linearly independent. So I'm going to calculate the determinant of this first matrix. And let me put the result right next to it, to the right. Other writing I might need to do. So the determinant of this square matrix is going to be, remember, we multiply these entries and we get 5. And then we subtract the product of these entries. So we do minus 6. And this is non-zero. If you get non-zero, this means that the 2 vectors are linearly independent. Let's make sure we read these instructions too. I kind of went through that quickly. Determine whether the columns of each matrix form a linearly independent set. If not, express one of the columns as a linear combination of the others. Okay, so because we get a non-zero determinant, these are linearly independent, which means it's not possible to write one column as a linear combination of the other column. In other words, it's not possible to write one column as a multiple of the other column. Now in this next case though, if we were to find the determinant of this one, we do 1 times 6, which is 6, minus 3 times 2, that's minus 6, so we get 0 this time. And I'm going to use C1 and C2 for the columns. So we're going to say C1, comma, C2 are not linearly independent. So you could also say that they're linearly dependent, or we say they're not independent, which means that, so in this case here, we want to express one column in terms as a linear combination of the other columns. Well, there's only 2 columns here, so I'm going to express column 2 as a multiple of column 1. So column 2 can be found by doubling column 1. Or you could also say that column 1 can be found by having column 2. Okay, this next case, we have a 3 by 3. It gets a little bit trickier when you have 3 vectors involved. The vectors are the 3 columns. Is it possible, for example, to produce this column out of doing some sort of linear combination of these columns? So like scale this one plus scale this one and turn it into that one. Is this possible to do? This is the question that we have before us. It can be tricky to think through that and try to turn 2 columns or do a linear combination of 2 columns to form the third. So let's just go straight to the determinant and see if we get a non-zero or a 0 determinant. Now I'm going to do cofactor expansion along this first column. Right, so if you recall, that means I'm going to cross out the 1 in the top left position. It's in the matrix of, the matrix of signs is a plus minus plus. I need to keep that in mind as I do this. And I'm crossing out a 1. So we get, this is equal to a positive 1. 1's in the positive position, so put positive 1, times the 2 by 2 determinant of the 2 by 2 matrix next to this. That's not crossed out. Then I'm going to skip the 0, because it's going to be 0 times a thing, times a determinant. Don't need to calculate that. And let's cross out now the 2. The 2 is also in a positive position, so we're going to have a plus 2. And then the 2 by 2 that's not crossed out is right there, 1, 1, 4, 2. Now I've got a few more determinants to calculate. Here we have 4 times 3 is 12, minus 8, that's going to be 4, and then times that 1, so we just get 4 out of this first part. And here we do 1 times 2 is 2, minus 4, so we do 2 minus 4, it's negative 2, times this 2 here, so we get a minus 4, and so we do get a 0 out of this. And this tells us that column 1, column 2, and column 3 are not linearly independent, or you can say that they are linearly dependent, which means that there's some way to generate one of these columns by doing a combination of the other 2. And see if we can figure out what that might be. And I think I see such an example. If you do 1/2 of the first column plus 1/2 of the second column, you will get the third column. So 1/2 of column 1 plus 1/2 of column 2 will give us the third column. And I should probably put these, call these column vectors, but I'm going to leave the vector notation off, just knowing that C stands for a column, hence it's a vector. Just being kind of inventing my own notation right now. But half of column 1 plus half of column 2 should give you column 3. Just double that, check that. Half of 1 plus half of 1 gives you 1, check. Half of 0 plus half of 4 gives you 2. Half of 2 plus half of 4 gives you 3. That works out. So column 3 is half of column 1 plus half of column 2, which means that we could also express column 1 in terms of columns 2 and 3. Just effectively take this equation down here and solve it for C1. And that will tell you how to use C2 and C3 to get C1. Or you can also make C2 out of C1 and C3. Just take this equation and solve it for C2, and that will tell you how to take columns 1 and 3 and make column 2 out of it. And then let's do one last one over here. Let's find the determinant of this 3 by 3. I'm going to do cofactor expansion along the first column again, because there's a lot of zeros there, and that's helpful. Or you can do it along this column here. Maybe do that column, or this row. I'm going to do, just for variation's sake, there's 2 zeros here as well, so I'm going to expand along that middle row, the second row. So when I cross this out, I'm crossing out a 0, so nothing to compute. When I cross this one out, I'm crossing out a 0, so nothing to compute. But now I'm going to cross out the 3, and you have to do the matrix of signs. The 3 is in what position? It's always positive in the top left, and then you do a checkerboard. So the 3 is in a minus position. So our determinant will be equal to negative 3 times the 2 by 2 that's next to it, which is 1, 1, 0, 2. And the determinant of that 2 by 2 matrix is 2 minus 0, which is 2. So we get negative 6 as the determinant of this matrix. Let me just show you that you get the same thing if you did a cofactor expansion along this column. Because here you would cross out the 1, which is in a positive position. So another optional way to do this is to get a positive 1 times a 2 by 2, which is 0, 3, 2, 1. And then you're going to get zeros everywhere else, so that's all we have to do. And the determinant of that 2 by 2 is 0 minus 6, which is negative 6, times that 1 in the front. So we also get minus 6. So you can see that it doesn't matter which, if I do cofactor expansion along the first column or if I do it along the second row. You get the same determinant. But the determinant is non-zero, which means that the 3 columns are linearly independent. So column 1, column 2, and column 3 are linearly independent. There's no way to make one column out of doing a linear combination of the other 2. Okay, now let's just take this up to where our matrices or our vectors have their functions of t involved. So the columns of a square matrix of functions are linearly independent if and only if the determinant of the square matrix is non-zero for some value of the independent variable. Determine whether the columns of each matrix form a linearly independent set. So we're just going to do this by using determinants and determining if the resulting determinant, which should be a function of t, is always 0 or sometimes not 0. So when I do the determinant of this first 2 by 2, we do sine t times 5, so we get 5 sine t. And then we do minus negative 3, so plus 3. So this is not always 0. In other words, there are t's for which this is non-zero. So there exists, at various values of t, we have a non-zero determinant. So then we say, we'll just say this is not always 0. So column 1 and column 2 are linearly independent. Now there are values of t where this where this will take on the value 0, but we just have to say that there are some t's where the determinant is non-zero. That is enough to say that the 2 column vectors of functions, one vector is a vector function, involves t, the other one is a vector of constants, but the 2 vectors, the 2 columns, are linearly independent because there are some t's for which the determinant is not 0. Now in this case here, if we do the determinant of this one here, we do t times 6t, that's 6t squared, and then minus 3t times 2t, that's minus 6t squared. And so we do get identically 0. No matter what t is, the determinant will be 0. So here, column 1 and column 2 are not linearly independent. There's a way to scale one column to make the other, in this case. And if you double the first column, you will get the second column. Or if you have the second column, you'll get the first column. Over here, let's do the determinant of this one that involves some exponentials. We do the product of these two here, 3 times e to the 2t, so 3e to the 2t, and then minus this product. Well, that product is 4e to the 2t, but we have to subtract that, so minus 4e to the 2t. That gives us a total of negative e to the 2t. And this is not ever 0. It's a little bit stronger than saying not always 0. Right, so we see 3 different cases here with these 2 by 2s. Here we got a determinant that was not always 0. Sometimes it's 0, but not always. We got one that's always 0, and we got one that's never 0. And in the first and third cases, we get to say that the columns are linearly independent. Okay, now we're on our last slide. Suppose we have a linear homogeneous system of ODEs. So the fact, these are bold x's, by the way, so these are vectors. And then we have a coefficient matrix, and we have a plus 0 over here, so that makes it homogeneous. Notice I'm not saying that this has to be autonomous, so there could be, it's possible that the coefficients of A have some t's involved in that matrix, but this is homogeneous and linear. The fundamental matrix is a square matrix where each column is a solution to the system, and the Wronskian of the fundamental matrix is its determinant. If the Wronskian is non-zero on some interval of the independent variable, then the columns are linearly independent on that interval, and they form the general solution for that interval. Okay, so this is going to be our key for forming general solutions as we move on to the future topics. And we have a system down here, a linear system. This is planar. It's only going to be 2 different dependent variables. We can say x and y. And we have 2 different solutions to this. This is a bold x1, by the way. So you could call this x1, y1. And then we have a second solution, x2, y2. This is a bold x here as well. So these stand for vectors. So we have supposedly two different solutions to the system given by these two vector functions. Okay, the first thing that we want to do is show that each vector is a solution. Okay, let's do that part first. And I'm thinking space-wise, how do I want to do this with space? Let's do it right here, step 1. Okay, so we're going to show that if I change this x to x1 and this x to x1, that this differential equation is satisfied. So I'm going to do this side of the differential equation first. So we take the coefficient matrix 5, 3, -6, -4, and multiply it by the x1. So we're testing whether or not this is a solution first. And the x1 is e to the 2t, negative e to the 2t. And when you multiply these together, we use vector matrix multiplication, right? So we're going to drag this out, so the e to the 2t will multiply by the 5, then negative e to the 2t will multiply by the 3, and I'll combine those. 5 e to the 2t minus 3 e to the 2t. Now I take this and I multiply it across the bottom row. So I multiply e to the 2t and -6, so -6 e to the 2t, and then multiply these two, so plus 4 e to the 2t. So this has the appearance, it looks square. This looks 2 by 2, but it's not. It's 2 by 1. There's only one column here. And I can simplify it as well. 5 e to the 2t minus 3 e to the 2t is 2 e to the 2t. And then the bottom entry will be negative 2 e to the 2t. The question is this also the same thing as the derivative of the first of x1? So here's x1. Now we're going to plug x1 into this side. So I've already done the right side of my statement. Now I'm going to plug in x1 to the left side of my differential equation. In other words, just do the derivative of this. And the derivative of e to the 2t is equal to 2e to the 2t, which is exactly what we have right here. And the derivative of negative e to the 2t is negative 2e to the 2t, which is exactly what we have right here. So this is the same thing as x1 vector prime. And let me stretch this over here a little bit and squeeze something into our notes here. So we started by doing a times x vector 1. So that's what we did here with this calculation, and we wound up with this, and it turns out that's the same thing as x1 prime. So we verify that x1, vector x1 that is. Be careful that vector x1 is not the same thing as term x1 or entry x1. It's very subtle. This x is not bold, this x is. That's why it's nice to have the little bars above the ones that are vectors, just to make it a little bit more obvious. And now I want to test that vector x2 is also a solution. So I'm going to repeat this process, but with this one here. And I'm going to do this side first. So this is still part 1, showing that these are solutions. So I'm going to do matrix A times vector 2. Okay, so matrix A is just our 5, 3, -6, -4. I'm going to multiply that by the second vector, which is e to the negative t and negative 2e to the negative t. This is a 2 by 2 times a 2 by 1. That's going to give me a 2 by 1 result. So I multiply the 5 and the e to the negative t first, and that's 5e to the negative t. Then I multiply the 3 and the negative 2e to the negative t, so that's going to be minus 6e to the negative t. Now I multiply negative 6 and e to the negative t, so we get negative 6e to the negative t. And then multiply these two entries, that gives us positive 8e to the negative t. This is a 2 by 1 that I just got, and it also simplifies the terms combined. And so we get negative e to the negative t, and we get 2e to the negative t. And the question will be, is this the same thing as vector 2 derivative? Well, let's verify that. Make that look a little bit better. Okay, so looking at vector 2, which is right here, the derivative of e to the negative t is negative e to the negative t, check. And the derivative of negative 2 e to the negative t is positive 2 e to the negative t, check. So we verified that x1 vector and x2 vector are in fact both solutions to this system. So we've done step 1. Step 2 is calculate the Wronskian of the fundamental matrix. So the fundamental matrix is just the matrix we form by putting these two solutions and making a matrix out of them. So we put x1 in the first column and x2 in the second column. So you have e to the 2t and negative e to the 2t. That's the x1 vector placed as the first column, and then we do the x2 vector placed as the second column, e to the negative t and negative 2e to the negative t. And then we do, this is the fundamental matrix. It's a matrix whose columns are solutions to the system, and then we found two vector solutions, and so we turned those two vectors into a 2x2 matrix, and we created a fundamental matrix. The Wronskian of this is its determinant. So now I'm going to do the determinant of this and see what we get. So we do that product there. We have e to the 2t times negative 2e to the negative t. Well, we're going to get a negative 2 coefficient, and then e to the 2t times e to the negative t, add the exponents. 2t plus negative t is just t. So negative 2 e to the t is the product I get from doing this diagonal, and then we subtract and we do this product. Well, that product is going to be just negative e to the t, but then we subtract that, so it's going to be plus e to the t. And then this simplifies to negative e to the t. And this Wronskian is never 0. And the interval on which it's never 0 is the entire interval. So all values of t, this negative e to the t is never 0. Now, let's go back up to the statement. If the Wronskian is non-zero on some interval, and this is non-zero on the entire interval negative infinity to infinity in this case, then the columns are linearly independent on that interval. So this column and this column are linearly independent. So the two solutions are linearly independent because the columns were the solutions. And they, meaning the columns, reading back up to here, the columns, form the general solution for that interval. Okay, so that's the next thing we're going to do is form the general solution. So we do any multiple of the first solution plus any multiple of the second solution, and that will be our general solution. So it's going to look like this. Some constant, C1. This is C1, not column 1, by the way. I know I've been using C's up here to stand for columns just to be lazy, but this C stands for a constant for creating a general solution. So C1 times x1, x vector 1 that is, which is e to the 2t, negative e to the 2t, plus some constant C2 times the second solution, x2 vector, which is e to the negative t, negative 2e to the negative t. This forms our general solution. So if we did have some initial conditions to satisfy, we would use this to try to define C1 and C2 so that our initial conditions are satisfied. But in today's lecture, we're not going that far. Just create the general solution. And then finally, step 4, show that the general solution is also a solution. Okay, so another way to write this general solution, just to be lazy, write it a little bit higher, is just simply write C1 times x vector 1 plus C2 times x vector 2. You can see it's almost better not to bother writing the components of your vector solutions as x1, y1. I never needed to use these notations. Let me just go ahead and delete that. Now we want to show that this is a solution to this differential, to this system of ODEs. So for step 4, we want to show, and let's call this general solution just x vector. So we're going to show that this here, which we're calling just x vector, is also a solution. So we want to show that x vector prime will give us a times x vector. Right. That'll show that this statement here is true. So we're going to change x vector prime to the general solution. So we have cx1 plus c1x1 plus c2x vector 2. We're going to differentiate that. And you're going to show that whether or not this is the same thing as doing a times and then c1 x vector 1 plus c2 x vector 2. Okay, well, if I differentiate the left side, you can just differentiate term by term. So we're going to get c1 x vector 1 prime plus c2 x vector 2 prime. And on the right side, I can distribute the matrix A and pull the C1, the constants C1 and C2 to the front of the products. So I can write this as C1 A times x1 vector plus C2 times A x2 vector. Now because x1 and x2 are separately solutions to the differential equation, the system, right? If I plug in x1 here, multiply it by a, then I get x1 prime. That's exactly what we just verified right up here. That a times x1 vector is x1 vector prime. So I can use that to change this to x1 vector prime. And I can do the same thing here. I can show that that's x2 vector prime, which I already showed above. Oops, I don't need the a there, sorry. And that shows, now we show that the two sides are the same. So that's all we really have to do. Check. This really just shows that this is the way that you would show in general that if you have two solutions to a homogeneous linear equation, system of equations, I should say, then any linear combination of those solutions will also be a solution to the homogeneous linear system of ODEs. All right, there's a lot of material here in this topic, so feel free to watch this video again as necessary to get these ideas internalized.